Hey guys, I've got another lesson for you. We're doing exponential growth and decay, and I'm going to talk to you a little bit about what that means first. So, as we have learned in the past, we were graphing lines, and when you have a line, it just makes a steady slope, rise over run. But now that we have exponents, so if I gave you a function 2 to the x, so now x is in the exponent, and so that's what makes it an exponential function, is the x is in the exponent. And when you have, so we'll make a little table here, and I'll show you what that means, 2 to the x, and there. If I do 0, 1, 2, 3, and we'll stick in a 4, and if I plug in these x's for the x, I get 2 to the 0, and that will equal 1 because anything to the 0 is 1. Then you have 2 to the 1 equals 2. 2 squared equals 4. 2 to the third equals 8. And 2 to the fourth, multiply 2 again, and that is 16. So here is a table of what happens to the numbers. And I also want to give you a visual of what happens. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. We're just going to get to 8 because I don't have enough room. But I'm going to go ahead and graph these. So the first one is 0, 1. And the next one is 1, 2. 1, 2. The next one is 2, 4. And that's about right there. And 3, 8 is way up there. And when I connect these, I can't even do the 4. It'd be way up there. Because notice what happens as we graph it. It turns into a curve and it rapidly rises. It goes up really fast. And so that's what we have for exponential growth. And exponential decay would be going in the opposite direction. So we'll talk about that on the next page. So that's a gist of what we're going to be doing on Monday. We're going to be graphing, and you're going to be getting these exponential graphs. So now I want to go ahead and tell you the formula. So we can just plug these in real easy, and you'll get to have the formula. So let's go ahead and write the formula. And so we've got y equals a times 1 plus, for growth, r to the t. So here is your formula. And over here, we're going to define what these mean. So let's see if we can get that going here. And I need to put a highlighter on it because we've got some lines here that I'm going to be drawing over. So A equals the initial amount, and it's always the initial amount. A is always the initial amount, that number out front there. In the next thing, we have R equals the rate, and we're going to make it as a decimal. And sometimes there's a decimal in it, and we'll just have to move that decimal. So it's not just drop the percent, it's change the percent. And then T is time. And so those are the three things that you need from the word problems. And so we'll go ahead and go to the first one. And I'm going to be giving you, like I said, I'm going to give you this formula so that you have it. Let me see if I get this. I'll put it over here. I'm going to put it right here so you can see it better. There we go. That'll be better. Okay. So my first A in this problem is 1400. And notice, well, yeah, and I want you to notice this, that it says increases right in the problem. That tells you that it's a growth. So if you don't know if it's a growth or not, then you need to go ahead and figure that out by the keywords, and growth is increase, and that's usually what they use. And these problems are all going to tell you about increasing money, like a savings account, your account balance increases, and then like a population can increase exponentially if you have a percentage of growth rate each year. And one thing that you have to watch out for is credit cards, because those definitely increase your debt exponentially. So be careful with those credit cards. Pay those off every month. All right, so we're going to go back in here and the percentage rate, and we're going to write that as a decimal. So R equals, and we move the decimal 2 places, so 0.09. It's not 0.9, that's only one place. You got to do 0.09 if it's a single digit. And then T, the time, is 25 years. So we want to know what the new amount will be after 25 years of a 9% investment rate. Okay, so we're going to put those into the formula. So y equals 1400 times 1 plus that percentage rate as a decimal raised to the 25. And all you have to do is put that right in your calculator. And when you put that in your calculator, you should get y equals 12,072.31. Now make sure you round to change because it is money, so you don't need extra decimals, just need those 2 places. And there's the first answer. Number 2, I'm going to go ahead and do number 2, another example. Let's see if I can get that a little bit better. No, that's not. All right, well, we'll see how it comes out. So this one, the initial amount is $12,000 tuition, which is pretty normal, but they're saying that this is increasing at a rate of 6% per year. That is actually pretty big. 0.06. So you're going to see what happens in 4 years if this tuition rate increases at 6% a year for 4 years. We're going to see how quickly your debt into college can increase. So y equals that 12,000, the initial amount. And then the 1 represents 100% because we're dealing with, so you start with the 12,000 and then you add the percentage to it. That's what's happening here in these formulas. So 0.06 at this rate for just 4 years. So just for 4 years, you plug that in and you get 15,149.72. That is your new tuition rate after 4 years. So that's a pretty big jump, especially with these big numbers. All right, we're going to go ahead down to the next slide and do a couple of decay problems. And I'll tell you, the formula is basically the same formula. It's just got a minus sign in it instead. So it is still the initial amount, and I'll write those again. 1 minus the rate, and it is still to the time. I'm going to go ahead over here again. We have A equals the initial amount. Again, it's all the same letters, so there's no change here. And rate as a decimal, and I'll fix this in a second, and time and years. So let me fix this, see if I can get that fixed. There, okay. All right, we'll do a couple of these examples, and the first one is a population, and it says the population is decreasing. So the decreasing, and the next one, depreciating. Those are the words you're going to look for decay. Makes sense. But again, we are going to go ahead and determine our initial amount. So the initial population here is not 2,000, that is a year. It was 1,300 people. So 1,300, so you got to make sure you distinguish. So 1,300 people was the initial amount. The rate that they are decreasing is 1%, so we're changing that to 0.01. And the time Well, it doesn't say the time. It says from 2000 to 2008. So that's 8 years. So it's not hard to figure that out. Some problems you might have to do that. And now let's stick it into our formula. 1300 initial amount, 1 minus for decay, 0.01, to the after 8 years. So y equals, and this turned out to be 1,200 people. And notice we want to go ahead and put our labels on these and round it to a whole number because it's people. And so there you go. That's number 7. I'll do one more. I'm going to do number 8. So number 8 is talking about the value of a car depreciating, which is totally what happens. A house increases in value depending on the neighborhood, but most of the time it increases in value. And a car depreciates in value a lot, quickly, so exponentially. All right, so our initial amount is the $18,000 price. The rate it depreciates is 12%, so we're going to write that as 0.12. And they want to know, what is the value going to be after 10 years? So put those into our formula. Y equals 18,000 times 1 minus 0.12 to the 10. All right. So the new value after 10 years, if it lasts that long, depending on the kind of car you get, the last value after 10 years is only going to be $5,013.02. And that's what happens. These I like these exponential growth and decay word problems because they are a glimpse of reality and they help you understand how money works. And that's about all I have. So the rest of these two worksheets here, rest of these notes / worksheets is your homework. So you have 8 problems to finish the exponential growth and exponential decay. And I'm going to be collecting all of these exponential problems, including the graphing that we're going to do on Monday, I believe. I'm going to collect them all on Wednesday the 1st, April Fool's Day. Yay. So you have lots of time to work on this. Let me know if you have any questions. Talk to you later.